Early space elevator concepts suffered from a specific failure point: the reliance on a single monolithic cable. If one section fails under the immense tension of orbit, the entire structure recoils and shatters into a cloud of debris. The V3.2 baseline moves away from this theoretical approach. We are now treating the tether as a verifiable materials engineering project, shifting the focus from physics thought experiments to a manufacturable discipline. This requires a commitment to a vacuum-qualified, dry architecture. Previous designs that relied on internal liquids or protective gels have been discarded, as they cannot survive the long-term realities of a vacuum environment. Low Earth orbit presents a range of environmental threats. Surviving them requires a layered architecture, where each functional subsystem is isolated and independent to protect the load-bearing core. We will construct this tether architecture from first principles, detailing how it manages mass and orbital hazards to enable a 100-kilometer surrogate test. Shifting to a dry, multi-layered architecture allows us to isolate the variables that have stalled monolithic designs. This provides a modular framework where individual layers can be validated before being integrated into a full-scale prototype. The structural foundation of this architecture is the primary load ribbon. It is fabricated from a continuous carbon nanotube, or CNT, quasi-unidirectional laminate. If this ribbon maintains a constant cross-section from the ground to orbit, its own mass generates enough internal stress to tear it apart before reaching a useful altitude. This graph illustrates the mathematical solution, the constant stress taper equation. By calculating the cross-sectional area as an exponential function of altitude, we equalize the load. Looking at the plotted curve, adjusting the ribbon's thickness at higher altitudes keeps total mass tightly bounded. As marked, this tapering strategy deliberately lowers the maximum required material strength down to 5 gigapascals. High-purity CNT composites in development currently show strengths between 6 and 10 gigapascals. By designing for a 5 gigapascal threshold, the material requirements move within reach of modern manufacturing. Tapering the ribbon aligns the tether's physical requirements with the tensile limits of modern carbon composites. This transforms the design from a theoretical impossibility into a problem of industrial scale and geometric optimization. Managing the stress on that CNT ribbon requires an internal monitoring system running directly along its neutral axis, where it can provide data without compromising the laminate's strength. We use an embedded optical fiber layer. This integrates discrete fiber Bragg gratings alongside distributed BOTDA sensors within polyamide-coated silica fibers. In this cross-section, pulses of light travel through the central optical core. These signals continuously monitor both physical strain and temperature changes across every meter. To maintain precision over vast distances, the fiber is divided into distinct zones. Each segment retains its own specific thermal and strain calibration constants, stored as digital data. Magnetic field diagnostics are kept strictly separate. These use independent Hall effect sensors to ensure electromagnetic readings never interfere with the primary optical strain data. Continuous segment-calibrated metrology is a requirement for any megastructure. It allows us to verify the integrity of the architecture before it is ever subjected to physical climber loads. Once the core is structurally sound, it must be shielded from the orbital environment, specifically microdebris and reactive oxygen. The first external layer is a Whipple-style shield. It is engineered to intercept and neutralize high-velocity particulates before they can impact the load-bearing ribbon. At orbital velocities of 7 kilometers per second, a tiny particle carries massive kinetic energy. Impacting the outer film, it instantly shatters into superheated plasma. An outer aluminized polyamide bumper triggers this fragmentation, while an open-cell aramid veil beneath it acts as a mechanical filter, catching the resulting plasma spall. This diagram shows the critical spacing required for this defense. The standoff distance between the bumper and the core ribbon is strictly maintained at 10 to 20 times the core's thickness. The secondary threat is atomic oxygen erosion. In low Earth orbit, this highly reactive environment causes rapid mass loss and embrittlement in standard polymers. We solve this by applying a 50-nanometer top coat of aluminum oxide or a fluoropolymer, which creates a chemical barrier against the orbital atmosphere. Beneath these protective layers, a dry graphite sheet or copper mesh acts as a thermal spreader, allowing the tether to reject heat without outgassing liquids. Standardizing this sequence of sacrificial and chemical layers provides a blueprint for orbital survivability that remains entirely within our vacuum-qualified dry baseline. Before a cable ever reaches orbit, it must survive testing in the atmosphere. Here, wind crossflows create a destructive resonance called vortex-induced vibration. To counter this, we morph the tether's cross-section. Shaping it into a thin ellipse or triangular wedge allows airflow to detach smoothly, suppressing turbulent vortices. This frequency chart demonstrates the result. This specific aerodynamic shaping achieves a 6 decibel reduction in vibration power near the critical shedding frequency. Terrestrial testing also requires a plan for structural recovery. If a segment is damaged during trials, the architecture must allow for a high-precision field repair. The repair protocol utilizes a double scarflap joint. To maintain the original strength of the laminate, this splice must extend 15 to 25 times the total thickness of the ribbon. The repair is bonded with low-outgassing benzoxazine adhesives. This ensures that even a field-repaired section remains compatible with the vacuum requirements of space. Mastering these aerodynamic controls and splicing techniques on the ground is a mandatory step before any tether system can be considered for orbital deployment. By integrating these layers, the development of the tether moves from a single vision into a staged validation matrix. Phases 0 and 1 focus on the basics, moving from 10-meter lab coupons to 100-meter outdoor tests to verify the sensing electronics and wind shaping under real-world conditions. Phase 2 scales up to a 1-kilometer continuous run. This stage is used to refine the taper manufacturing process and to drill the high-precision splicing procedures. The roadmap leads to Phase 3, the launch of a 10 to 100-kilometer surrogate. This tether will reside in LEO to provide long-term data on impact resistance and chemical degradation. These surrogates are intentionally simplified to exclude climber loads. Their sole purpose is to isolate and verify the structural survivability of the tether itself. This iterative approach proves that the path to megastructures is not found in a single leap of faith, but through the relentless application of